The next speaker is Bruno Oliveira from Hong Kong University. He will talk about the inexact superclass problem. Yeah. Please go ahead.
Okay. Okay. Thank you very much. Thank you very much for inviting me to the UNSOUND workshop. So this talk is about the inexact superclass problem, and let me start by giving a little bit of context about what the problem is about. Basically, this is a problem that arises when we try to type check dynamic inheritance. Okay, so this talk is going to be about inheritance as we see it in object-oriented languages, and in particular, one flavor of inheritance that we see typically in dynamically typed languages, which is this dynamic inheritance flavor. So dynamic inheritance is a common feature in several dynamically typed languages, including JavaScript. So the examples that I'm going to present today are JavaScript and TypeScript programs, essentially. Dynamic inheritance is not a common feature in statically typed languages like Java or C#. Those languages basically have mostly avoided dynamic inheritance, and they use a different variant of inheritance. And mostly they avoid it because of some typing difficulties. However, TypeScript, which attempts to type check JavaScript and has a very rich type system that tries to type check as many JavaScript programs as possible. It supports some mechanism that type checks dynamic inheritance. And what I'm going to show today is that this mechanism is essentially type unsound. And I'm going to analyze the problem a little bit. Why is it type unsound? What are the difficulties? And also point out that the problem is a general one. So if you ever plan to have a language that has a type system that tries to type check dynamic inheritance, you probably have to face this challenge. So basically, the inexact superclass problem gives you a canonical example that illustrates the challenge. And it also illustrates the unsoundness issue that you have in TypeScript. Okay, so let's dig into some background explaining what is this about static and dynamic inheritance. What are the differences? As you know, inheritance is a key feature in many object-oriented languages. It's used for reusability and to extending existing classes. And in this talk, we are going to consider two flavors of inheritance. One is static inheritance, which probably most of you are familiar with. And in static inheritance, the inheritance hierarchy is determined statically at compile time. Okay. And then we have dynamic inheritance. And in dynamic inheritance, you have a more flexible form of inheritance where the actual inheritance hierarchy can be determined at runtime. So let's be concrete. Let's look at some programs. Let's look, for example, at this typical Java program here. So here we have a class A with a method greet. Okay, so we defined class A with a method greet. And then we have a class B, which extends this A, so it's a subclass. And here we can see the inheritance. We can see this keyword extends, and we say that B inherits from A, for example. So it's going to inherit all the method implementations from A. Of course, in this case, we are overriding greet. So basically, we inherit, but we immediately override. So there's no other methods that we inherit. But it also shows another feature that you normally have in object-oriented languages, which is not just the ability to inherit but also the ability to override some existing implementations, right? So this method here is overriding the greet method and replacing the implementation with some different implementation. Okay. An important point here, which is related to why we call this static inheritance, is basically that when we have this class declaration, the syntax that we can use here, so class B extends A, in this syntax, the A here is restricted to be essentially the name of a class. Okay. So in particular, so you don't have the flexibility to write other things here. You cannot write another expression or a type that is not a class, etc. So all that you can write here is essentially the name of a class. Okay, so you might have a little bit of flexibility if you have generics. So you might have class with arguments, but essentially you have to write the name of the class plus the type arguments. Okay, so because you write this name of the class, that means that what you're extending is statically known. So you're extending exactly this class A here. Okay, nothing else. So that's what we mean by static inheritance. So now let's try to contrast this with dynamic inheritance. Actually, before that, let me just summarize some things about static inheritance. But so this is just a summary. So essentially what happens here is that in static inheritance, we have a statically known superclass. Okay, as I just said, when we have this syntax, class B extends A can only be a class name. So this implies that A is always statically known. And the other thing that is important to mention, or one other thing that is important to mention, is that class declarations have a dual role. Okay, so if we come here, so a class declaration declares both a type. For example, there's a type called A whose interface contains a greet method that returns a void. There's a type called B whose interface returns a greet method, return void as well. Okay, so class declarations serve this purpose of declaring a type, and they also serve the purpose of providing an implementation for that type, right? So here, in addition to declaring a type that has a certain interface, you also provide some implementations. Okay, so there's a dual role in these class declarations, and one thing to notice here about this dual role is that there's a tight coupling between this type that we are creating and this implementation. They are inseparable in some way, right? So here, when we say class A contains these methods, we are both defining the type that has this interface together with these concrete implementations. Okay, so now we can move to dynamic inheritance and see how it's different. Basically, dynamic inheritance is supported by many languages, including JavaScript. And here we have an example of dynamic inheritance in JavaScript. So we can have a JavaScript function, and this function is called mixin. And mixin is parameterized by base. Base is just a function argument. And then what this mixin does is that it returns a class. So it creates a class. Okay, so it creates a class, and the class that it returns is a class that extends base. Base is the superclass here. And what is base? Well, base is just this argument to the function. Okay. So what this means is that this class is going to be created at runtime. So we are going to create this class at runtime, and the super class of this class is going to be provided as the argument of this function, right? So you're only going to be able to exactly determine what the super class of this new class is at runtime after you run this function application here, right? So here, this class extends base, and it's a class that is going to have this greet method. And here, differently from what we have in static inheritance, we have that base is just a regular program variable, right? So it's not the name of a class, as in static inheritance. It's just the name of a variable. And in fact, in JavaScript, you can here at this position, you can write an arbitrary expression. So you could have an expression, for example, another expression that, let's say, a function call that then returns a class. Okay, and that class is going to be the superclass of this new class. So essentially, here we say that this is dynamic inheritance because the inheritance is going to be determined at runtime. So it's not statically determined, but it will be determined at runtime. Okay. So to summarize, to give you a summary of the characteristics of dynamic inheritance, one characteristic is that the superclass is determined at runtime. And in particular, you can parameterize over the superclass. So you can pass a base class as an argument, and then create a new class with that base class there in terms of inheriting from that base class. So another interesting point is that when you have this flexibility, then you get this notion of a first class. Okay, so in most in languages like Java, C#, and so on, traditional languages, classes are second class. Okay, so you cannot pass a class as an argument. You cannot create, you cannot return a class from a method or a function. Okay, but when you have dynamic inheritance, typically you also have first class classes. You can pass classes as arguments. You can return classes, as we can see here, as results. Okay, so they are first class values in exactly the same sense as first class functions in functional programming. Okay, and this gives you greater flexibility. So it enables various very dynamic forms of inheritance. You can have dynamic mixins, dynamic traits. You can even have virtual classes and family polymorphism. Okay, and another interesting point is that unlike static inheritance, where you have this very tight coupling between the class type and the implementation, so here you decouple the class type from the concrete implementation, and we will see that this here is important for the inexact superclass problem. Okay, so now I told you about JavaScript. So this is dynamic inheritance in JavaScript. So let me tell you now about TypeScript. So tries to type check this dynamic inheritance. Okay, and here we can see an example, and I'm going to explain a few more things about this in the next slides. But we can basically annotate the JavaScript code that we wrote previously with a few additional types. In particular, now the function mixin gets parameterized by a type, so this t-base, and this type t-base extends constructor. Okay, and constructor means that basically t-base is essentially a class. Okay, so basically this constraint is saying so that T-base is the type of a class, basically. And now we say that base, our argument to this function, as the type of base is T-base. Okay, so here we essentially know the interface of the superclass. The interface of the superclass is this T-base, and base is the implementation, if you wish, of the superclass. So here, in TypeScript, now we can write, we still write the same code. So we still write that class extends base, and that this base has this T-base interface. So how does this work? So let me just tell you a few more things about this. So as I said, this constructor, so here is not very important to understand the details, but it basically says that constructor is something that can be instantiated with new. So you can use new with some arguments, and it's going to return you an object, essentially. But to abstract things a little bit, you can just think of this type as representing a class that can be instantiated with any number of arguments and returns an object. So this kind of pattern and idea is documented in the TypeScript documentation. So where they use they use the name mixins. So they call this code structure that we have been using before mixins. And what they are documenting in this web page here is how you can type check the mixins in TypeScript, and basically this constructor is documented there. Okay, right. So this is how TypeScript type checks the first class classes. Okay, and now before I go into the inexact superclass problem, I want to talk about one more thing, which is overriding. Okay, so I want to go through overriding in JavaScript, and I want to go through overriding in TypeScript. So in JavaScript, okay, JavaScript is a dynamically typed language. So overriding is completely unconstrained. Okay, so there are no constraints on overriding. And essentially, methods in subclasses can override methods in superclasses with different types. So we can see an example here. So we can have a class A that has a method M that returns 48. So here 48 is a number. Okay. And then we have a subclass, class B, that extends the A. And now we are going to override M. And we are just going to return a string. Okay. So here we return a string. Obviously, there's no problem doing this in JavaScript. JavaScript doesn't have a type system. So this is fine. So it's allowed. And now you would have a class B where the M returns a string. So this is clearly not type safe, right? Because you're actually changing the interface, at least if you have some expectations. But anyway, that's not a goal of JavaScript. So nothing to worry about at this point. How about TypeScript? So TypeScript needs to be a bit more careful because it has a type system, and it tries to ensure type safety. And the way that TypeScript works is not that different from the way that Java, C#, C++ works. So it has some restrictions on the overridden methods to ensure that these overridden methods have compatible types. So the example in the previous slide does not type check in TypeScript. TypeScript is going to complain that the type of M is not compatible. And here we can see an example that does type check. So obviously, if you have a class A with a method M that returns 48, a number, you can override, you can create a class B that extends A and then overrides M to return another number. So in this case, this works, of course, because the types F compatible are compatible. Okay. So now we can finally move to this inexact superclass problem. So what is this problem about? And so this problem, as we shall see, arises because the exact type of the superclass is unknown at compile time. Okay, so basically you have the flexibility to pass an implementation of the superclass, and you have the and you can specify the expected type of that superclass, but these two types don't necessarily have to match the actual type of the superclass with the expected type of the superclass. They don't have to match, okay? And in particular, the actual type of the superclass may be a subtype of the expected type of the superclass. And this is a key difference compared to static inheritance here, okay? And it can lead to type-safe overriding, and that's what I'm going to show you, okay? So, then let's look at the inexact superclass problem with a concrete example. So here, what we have is a class A. This is going to be our superclass, okay? So class A is going to be our superclass, and this class A defines two methods. One method M that returns a string, and one method N that calls M. So here, this is quite important. So you call M, and here, of course, you're expecting a string. So you're calling some methods that rely on M returning a string. So the important point here is to note that N depends on M via self-reference, okay? And it's expecting that the M returns a string. So now we are going to try to create a subclass using dynamic inheritance. So we are going to write a function mixin that is similar to the function mixin that we wrote previously. Okay, so where we are parameterizing the mixin by the superclass, and we are saying that we have a certain expected type for the superclass. Okay, and here this t-base doesn't say much. Okay, so it just says that there's a superclass, and basically superclass here doesn't expect anything in the superclass, doesn't expect any methods. TypeScript does allow you to specify a concrete interface, okay, but this doesn't matter. So you could say that t-base contains an A and a B and so on. This is allowed, but actually we will see that this doesn't matter for the inexact problem. Okay, but here basically the t-base, just think of it as the interface of the superclass. Okay, and here now we define a class, and we define it to have a method M. But of course, by the semantics of JavaScript, so what happens here is that if it so happens that this base actually contains an M, this M will be overridden. So, so here, when we are writing this code will have the ability to override any M that is in base. So if there's an M in base, it's going to be overridden. Okay, and that's another important point to remember. So here, then after defining this mixin, we are going to instantiate mixin and A. So we are going to basically create a class B, and this class B is going to be the resulting class of running this mixin parameterized with the A. Okay. So the important thing to remember is that A as an M of a different type, as an M of type string in base. So that M is going to be overridden. Okay, so you create a new class that extends the A. You're going to override the M in that class. You still contain the N. Okay, so now what's going to happen? So now what's going to happen is if you try to instantiate B, okay, so this B is going to be a class that contains this implementation M and this implementation N here, okay? And this is going to give you a runtime error because now N is going to call M and expect that the M gives you a string, but the M that you actually contain gives you an integer, okay? And this is basically the issue that happens here. The inexact superclass problem. Okay, I think I should, in the interest of time, I should go ahead. So this part I already explained here. So let me just go to this slide here. So it's useful to take a step back and just see what features are needed to trigger this problem. So basically, we need self-references. Okay, so the self-references are needed because the superclass relies on methods that depends on other methods, and we need inheritance, dynamic inheritance. Okay, and it's useful to mention that multiple inheritance would make this problem worse, but we don't have to worry about that in this talk. Okay, so but basically once we have self-references and this dynamic single inheritance, we are likely to have this inexact superclass problem. Okay, so I think I can skip this. This is the final slides. Okay, maybe possible solutions. One solution is stick to static inheritance. Okay, so static inheritance doesn't have this problem because you don't have the flexibility to decouple the expected type of the class from the exact type of the superclass. You could try to impose some restrictions. You could remove self-references. That would be probably too restrictive. There are some other, perhaps less restrictive things that you could do. And the other thing you could do, and this is, for example, one of the lines of work that I work on, is you can try to make the dynamic semantics enforce information hiding and having some other types of constraints, disjointness constraints. And there are solutions along these lines, so I've been working on them. The CP language, which is one programming language we develop in my group, for example, provides a solution for this inexact problem. Okay, and okay, I think I will stop here. But basically, the inexact superclass problem highlights this type safety issue that can arise with dynamic inheritance. So if you want to create a language that supports dynamic inheritance, you probably need to pay attention to this issue. Okay, and I'm ready for questions.
Okay, thank you. We have a question.
I don't know if these are questions or comments. First of all, this is nice to draw attention to this problem, and I didn't know you actually had a system that actually solves it. This is Gilad Brock. I've thought about this in the context of type checking Newspeak, which of course would have this problem if you tried to type check it. I guess when you say enforce that only the statically known information is known, that implies that when someone tries to pass in a class, you're going to be able to check that it somehow violates that by having extra methods that might, because it's not only that they could conflict, you could have extra methods that are added later in an overriding subclass somewhere that you didn't know about, and they could conflict with whatever methods you happen to have in the incoming class. So I assume you're taking care of all that. And And a meta comment, I assume you know, this goes back to the record calculi of Mitchell and Cardelli from like 89 or so when they did record update and
Yeah,
they
this
found
one.
out that doesn't work. Last
Yes.
comment, I'm not sure, but your JavaScript example might just end up working because JavaScript might turn the integer into a string.
I think this one doesn't work because it's a method call. I remember trying this. I did have an example before where it had just worked because JavaScript does lots of implicit conversions. I would double check, but I believe in this case we checked that because we had some previous examples like with integers and strings where JavaScript would just convert the string to an integer. Okay, and that works because it does this implicit conversion at runtime. But I believe that this one, I'll double check, but I believe that this one gives you that it doesn't contain the method.
Okay, cool.
Okay. Yes.
Yeah, you were about to say something.
I was just going to comment a little bit about maybe CP. Yeah. So basically, CP, what it does is that it has an unusual semantics. So it's a bit unusual, and there's basically subtyping there is coercive. So when you have an upcast, actually it creates kind of a proxy around the original object, if you want, that will hide all the extra information that you shouldn't rely on. Okay, and that's basically what this sentence here means. So that's quite unusual compared to other programming languages.
Okay, so we have another question.
Hi, yeah, this is Madhu Sridharan. This is pretty cool work. One other point in the design space I'd be curious about your thought on. It doesn't give you static safety, but the fact that you, in this code example, it's kind of called a mix-in, which to me implies that maybe the intent was that M is not supposed to be overriding something from the base class. And if you look at, say, Racket's object system, you have to explicitly, when you're declaring a method in a class, declare whether you intend to be overriding something from your superclass or not. And if you didn't do that in this example, you would still get a runtime error, but you would get it at the point when you invoke mixin rather than later on when you invoke n. So it doesn't give you static safety, but
Okay.
there's just another point in the design space where you might get a more, I think, sensible error, because again, I'm guessing the intent in writing this mixin function wasn't that M would be overriding a method.
Mm-hmm. Right. So that wasn't the intent. I think this could happen accidentally. That's the point, right? So it could be that by accident your subclass implements more methods, and by accident they clash with the your superclass implements more methods, and by accident they clash with what you have in the subclass. So I do know that Racket also supports first class classes, so they have a different approach and different solution. I don't remember now the details, but yeah, thank you for pointing out.
Sure. Yeah. In Racket, I think you would get an error right at this method call that you've highlighted.
Okay. All right.
All right. Any other question from the audience? I also had a question that it seems you didn't list all the possibilities to fix this problem, which you could also be more specific in the type system, right? More specific about the class that you want to mix in. And in fact, I think you could express this requirements on the base class using our system supergroup. You would just need to specify as an annotation in the base class type the requirements that this base class is allowed to make on the this value. Does this make sense to you?
I think that is related to let me see. I had a sentence about that. Right. So I think it's related to this point. So basically, you're saying. So you're saying specifying the requirements on the superclass, right?
Yeah, yeah. So in our system, if you want to define a mixing component that uses this binding, it needs to be explicit about what it needs from this, and so that becomes part of its type, right? And you cannot. So you would have to have to parameterize the base class with the requirement it needs on the this binding, basically.
So that is also supported in TypeScript. So TypeScript also supports this. It's so they basically have a generic version of this constructor here. I didn't show the code with that because it's a bit more complicated. But they have a generic version of this constructor here, which has a generic argument that then you can use to specify the interface that you want for the superclass.
I didn't know they had that. Okay. Mm-hmm.
They have that.
Cool.
So it's in this web page. Is in this web page here. Okay, so if you go there, I think it's called gconstruct.
Okay.
In that web page, and but it doesn't help. It doesn't help. Because the point here is that, okay, you can say that the interface of the superclass contains two methods, right? So, and so on. But here, this point is related. You have to anticipate. So in the superclass, of course, you're going to create a superclass that is is a subtype of the expected type. So you can create whatever methods you want, as long as one. So it might contain those two methods that you expect, but it can contain other things, right? And if one of these other things that it contains is a method of that is overridden here, then you get the same problem. So specifying.
Well, but if that method is being used in a way that would be problematic, it would appear in the interface that's expected of the this instance. In order to call anything on this, you would need to specify that as part of the this annotation. In our system, at least, if you want to use this, you need to say what you expect this the type of this to be.
Yes. Okay. So maybe you have a mechanism for that in Super OOP. So you're saying that when you use the this in Super OOP, so you're saying here, right? So here you would specify that this can only call.
Yeah, you would say the type that this must have, and then this should be matched with whatever the subclass wants to create as the final this value.
But in here, for example, if I specify this class, I would say that this can call M.
Yeah,
right?
Yeah, and the type you expect from that.
Right. But so you could say that, okay. And for simplicity, let's assume here T-base just says, I only expect that the superclass is empty.
Yeah, if
right?
you do that, then you cannot upcast A to this, right? Because you cannot get rid of these requirements are contravariant, right? You cannot get rid of them.
Okay. All right. So I haven't checked that part of Super OOP, but if you have
so to be clear, Super OOP doesn't have first class classes at this point, but it's like a natural extension, right?
Right. Maybe it's a solution.
I think it's another design point in the many solutions you propose.
Okay.
Yeah. Okay, cool. Thanks for the answers. I think we're out of time, right? So let's stop here and let's thank Bruno again.
Thank you.
Okay, thanks for joining remotely, and I'll talk to you later.
Yeah. All right.
Bye-bye.
See you. Bye.